We're going to continue on with our survey of the periodic table, and now we are moving on to groups 5A and 6A. Other way of naming these are groups 15 and 16, highlighted here, and that would be the oxygen and nitrogen families. Okay, so starting with group 5A or 15, the nitrogen family. Here are the elements, and a little bit odd because they chose to show nitrogen as a liquid here, liquid nitrogen. But really, at room temperature, its elemental form is N2 gas, a diatomic gas, and it's one of the major component of our atmosphere. But yeah, for whatever reason, they're showing it as a liquid. Phosphorus is kind of this red, in one of its forms, can be this kind of red rock-like substance. Arsenic sort of looks like a silvery rock, and same with antimony, really. And then bismuth has this really kind of cool crystal structure and like iridescent color. The interesting thing about this group is that it's one of those groups that has a name. And we'll talk about the halogens next lecture and the noble gases. But you know, a lot of these groups, we don't really have like a specific name for them, but this group we do, and it's spelled a little bit funny here. This is the name of that group, and the P is sort of silent, so this is pronounced Nicogen, the Nicogen family. Where that name comes from, I don't really know. Right. These all have valence electron configurations of S2P3. This group has more similarity among the group than previous groups, and that's something that trend will kind of continue as we move on in the next groups as well. Okay, so when we look at the Nicogen family, nitrogen is at the top. It's a diatomic gas, very low boiling point, right? That's due to the very weak intermolecular forces it has. Phosphorus exists most commonly as a tetrahedral P4 molecule. It has stronger dispersion forces than N2, so not a gas, right? It's a solid. Arsenic exists as extended sheets of arsenic atoms covalently bonded together, so it has covalent network bonding. Antimony also has that covalent network structure. And bismuth is really metallic bonding. Right? And its melting point is lower than that of arsenic or antimony. So it is becoming more metallic down that group. And that transition from non-metal to metal happens there. Right, so some patterns of behavior in this group. Nitrogen gains 3 electrons to form the anion N3-. That's only in compounds with active metals. The lower elements in the group are metallic and lose electrons to form cations. So now they are not gaining electrons anymore, they're only losing them. Oxides change from acidic at the top with nitrogen to amphoteric and then to basic as you move down the group. Right, and that really just shows you the metallic character is increasing as you go down that group. All group 5 elements form gaseous hydrides with the formula EH3, where E is a member of that group, and they form bonds to 3 hydrogens, and all these molecules are gaseous. Okay, NH3 is the exception here. It's not extremely toxic and reactive. All the others are. So if we look at uniqueness principle with respect to these hydrides, right? NH3 is a covalent hydride with a pyramidal shape. PH3 also same shape, but does not hydrogen bond in water. So there's some differences there between NH3, which it undergoes hydrogen bonding very extensively, and PH3, which does not. Arsenic H3 is much less stable and decomposes when you heat it to form arsenic solids. So this is much more reactive than the other two, right? So even though they're in the same group, they form similar molecules with similar formulas, but these molecules have very different properties. Right, so nitrogen, if we look at nitrogen N2 gas, this makes up about 80% of our atmosphere. So a vast majority of the atmosphere is this N2 gas. The small size of nitrogen allows it to form that triple bond. Again, the nitrogens are small enough that they can get close enough to each other where the atomic p orbitals that are not hybridized can overlap to form pi bonds. Right, much like carbon and oxygen in the next group, which we'll see, they can do this type of bonding, multiple bonds. Right. Nitrogen's stability makes it an inert gas, so it's not very reactive at all, which is why we call this an inert gas. Right. Reactions that form N2 gas as a product, therefore, are extremely exothermic and explosive. And that's because N2 is very, very stable. So the reactants that make it in a relative term are sort of unstable, and it will give off a lot of energy when that is produced. And one of those such molecules is TNT, nitrotoluene. These reactions are highly exothermic, explosive, and N2 is the product. So here's the molecule TNT. Okay. Don't need to remember this or memorize it for this class, but when this reacts, it forms 3 moles. For every 2 moles of that, you get 3 moles of N2 gas, and then we got water, carbon monoxide, and then solid carbon as well, which is kind of interesting, right? But this reaction is extremely exothermic. So if you look at the delta H of the reactants compared to the products, the reactants are much, much higher than the products. So this heat is released, right? Delta H is negative, heat is released. Right, some other high sort of explosive nitrogen compounds. Hydrazine, this is used as a rocket fuel. So a pretty simple structure. You have 2 nitrogens and each are bonded to 2 hydrogens. And when this is mixed with N2O4, it makes N2 gas and H2O. Right, again, very exothermic. Nitrogen can be in liquid form, N2, not just a gas. So it has a boiling point of about 77 Kelvin. So you have to cool it down substantially to get it into that liquid form. Right. It's relatively inexpensive, though, because it is so abundant in the atmosphere. So you can have industrial processes where you compress down nitrogen gas enough to make it a liquid, okay, and then you can use the liquid nitrogen to cool things. And its primary use, there's medicinal uses for it in instruments that need to be cold. Scientific in labs, there's lots of uses for liquid nitrogen to cool things down. And there's actually also culinary applications, right, in the kitchen. And so that's kind of what's shown here in this blender. Well, nitrogen fixation is a term that we use when you convert molecular nitrogen, N2 gas, into nitrogen compounds. And that's, our bodies need this to happen. And we'll talk about this in a second when we talk about the nitrogen cycle. But really, all life on the planet is dependent on nitrogen being fixed, that is, being converted from the N2 gas into molecules that our cells can use. And so in agriculture, we need nitrogen as a fertilizer source. And this is the industrial process that happens to make this happen. So you use N2 gas with hydrogen gas and you produce NH3. Okay, this is known as the Haber process. And again, it's making ammonia gas. Okay, this reaction is not the easiest. It has to be 500 degrees Celsius at about 500 to 1,000 atmospheres of pressure, and then you also need an iron oxide catalyst to do this. Okay, not super effective, but or I shouldn't say that. It's not super easy, but it is a very effective method. And by doing this this process, by developing it, he really revolutionized this ability to create synthetic fertilizers, which increased crop production and food production a great deal. Nitrogen's pretty unique in that it can have a lot of different oxidation states. It can vary from -3 to +5, so that's a giant range. Right, so if we look at, we're going to see examples of all these oxidation states. So in the -3 form, ammonia, NH3, nitrogen would be in the -3 oxidation state. Hydrazine, that was that component of rocket fuel that we looked at. And 2H4, it's in the -2 oxidation state. Hydroxylamine, we don't really talk about this, but this would be an example of a nitrogen in the -1 oxidation state. Nitrous oxide, that is laughing gas, so that's N2O. It is in the +1 oxidation state. Right, so laughing gas used as a surgical anesthetic. It's also used as a propellant in things such as cans of whipped cream. Right, and so there's actual nitrous oxide in there. Right, I would not recommend huffing that in the form of whippets. Right, because it can be very damaging to your brain if you do it too much. So just be aware of that. And it also kind of ruins the whipped cream. You run out of the propellant and then it just kind of like liquid comes out and not as good. Nitric oxide, NO, is nitrogen's in the +2 oxidation state. And this was fairly recently. It was discovered in the early 90s that this is a neurotransmitter and it regulates blood pressure, among other things. So that's why it won the Molecule of the Year in '92. Okay, so very, and what you'll notice about it is that it's actually a free radical. So it has one unpaired electron, which is fairly unique in molecular terms. These are usually pretty reactive, but this is an example of kind of a more stable free radical. Okay, here's examples of the +3, +4, and +5 oxidation states in nitrogen, and they're all nitrogen oxide compounds. Nothing really to say about any of these, though. Okay. So if we look at some oxides of nitrogen, it forms 6 stable oxides. The delta H of formation for all 6 oxides is positive, and that's because N2, that triple bond of N2, very, very strong and very, very stable. So forming any oxides from that, that delta H is going to be positive because you're starting at such a low potential energy for N2. Right. So NO is produced by the oxidation of ammonia. So if you oxidize ammonia with O2 gas, you get NO plus H2O. Right, this is, by the way, the first step in the production of nitric acid. Right. NO can be converted to 2 other oxides by heating it, and you can get N2O nitrous oxide, or NO2, nitrous oxide. Nitric oxide, nitrous oxide, and nitric oxide. This type of reaction here, where you kind of split one molecule into two, it can be termed a disproportionation. This is a redox reaction, and so you're splitting one molecule, and you're getting one that's more oxidized and one that's more reduced. I should say this one's more reduced, this one's more oxidized. Okay, so that's where the term disproportionation comes from. Probably not going to need to know that for this class. You might see it again later, especially in biochemistry. Right. NO2, that's a component in smog. So when there's like a brown cloud from pollution, that's usually caused by NO2. Not as big of a problem anymore because of more technology and emission requirements, but it used to be a much bigger problem. Okay, so here is just a structure of the 6 stable oxides that nitrogen can form, right, with some properties if you're interested. And the oxidation states are listed. So nitrogen also, when it combines with oxygen, can make acids, oxoacids and oxoanions. Nitric acid is probably the one we're most familiar with. That's HNO3. It's produced by what's known as the Ostwald process. Probably don't need to know this for this class, though, but you're using NO2 as the starting point. Nitric acid, it's a strong oxidizing agent as well as a strong acid. So when you put this in water, dissolve it in water, you get the nitrate ion. And this acts as the oxidizing agent. Nitrous acid, now this is, instead of HNO3 and nitric acid, it's HNO2. Right, so this is nitrous acid. It's much weaker of an acid, and you might remember this from the second quarter of the course, talking about weak acids and weak bases, so this was an example of a weak acid. Follows the general pattern for oxoacids. The more oxygen atoms bonded to the central nonmetal, the stronger the acid, right? So you have 3, that's a strong acid. You have 2, that's a weak acid. And just a picture of this. When this nitric acid gives up that proton, this is the NO3 minus nitrate ion. When nitrous acid gives up its proton, it makes this nitrite NO2 minus ion. Right? The difference here, the geometry is different, but probably more importantly is the fact that strong acid, this dissociates completely. This is a weak acid, so it's in equilibrium, and not very much of this forms when we put it in water because it is a weak acid. So then, much like the carbon cycle we talked about last lecture, nitrogen has a cycle. So the nitrogen cycle involves direct interaction between land and sea. Atmospheric nitrogen must be fixed to enter the land and sea. Right. Atmospheric fixation occurs when lightning provides the energy for the reaction between N2 and O2, so nitrogen can be fixed naturally without a biological source of the fixing. That the amount that's fixed that way, I would hazard to say that it's probably fairly minor in the grand scheme of things. Industrial fixation, we talked about that, producing ammonia. That's one of the ways that it's industrial fixed, and that's primarily to make fertilizers. And there's also probably the most important way, at least for us, is biological fixation. This involves conversion of that atmospheric N2 to things like NO3 by things like blue-green algae and nitrogen-fixing bacteria. Right, so there's relatively low numbers of things that can do this, and because of that, they're very important. If they were to go extinct, life on this planet would be in great risk of dying out, because all living things need nitrogen. We need nitrogen primarily in our proteins. Okay, so there has in living things, most living things can't do this by themselves, so they're reliant on nitrogen fixing bacteria and blue-green algae to provide these compounds, which then can be taken up by plants and then into animals. Okay. There's also the opposite of that, denitrifying bacteria. They reduce nitrate back into N2 gas, okay, to allow it to cycle back. That way, if you didn't have this step, you could see how, over time, the nitrogen in the atmosphere would just be going down and down and down, and all being fixed into these other compounds. Right, so here is the picture of the nitrogen cycle. Again, for this class, you don't need to know it in great detail. It is, very important. And the one thing I wanted to mention about this is, those primarily, I don't know if this is doesn't really show it very well, but I think here's the point that I wanted to make. You have this biological fixation, and that's based on typically bacteria that live in the roots of some plants, in particular legumes like beans. So a lot of people say that those plants are very important for nitrogen fixation, which is sort of true, but it's because they have these bacteria that live on their roots. And deeper in the soil on the roots, there's very little oxygen around, and so that's how these bacteria can function as nitrogen fixers. If there's oxygen around, that reaction doesn't really work as well. Okay. Right, so they get fixed into the soil, and then other plants can uptake that nitrogen from the soil, produce the nitrogen-containing compounds that animals can eat, and then animals ultimately the nitrogen gets cycled through them and excreted in the form of something like urea or ammonia if you're a fish, right? And then they can get reacted back to nitrates, and this cycle can continue. Okay. Moving down in that group, the next element would be phosphorus. Phosphorus has 3 allotropes of it. Okay, most common is P4, and it's in this sort of tetrahedral shape where all vertices of that tetrahedron have phosphorus on them. Okay, so that would be P4, also known as white phosphorus. Red phosphorus is another allotrope, and it's kind of like these connected to each other, so a string of these. And then you have black phosphorus, and you can see in black phosphorus, it's this more complex network covalent bonding structure. There are some oxides, more complex oxides that you can make with phosphorus. P4O6 has phosphorus in the +3 oxidation state. P4O10 has phosphorus in the +5 oxidation state. So you can see that, sort of like nitrogen, you can have multiple oxidation states in phosphorus as well. Okay. The oxoacids of phosphorus are important, and we've seen some of these. H3PO3, right? So we have 3 oxygens attached to phosphorus, has 2 acidic H atoms, so 2 protons can come off. So that's a diprotic acid, right? So this is phosphorus acid, The other acid, oxoacid from phosphorus that we see commonly is H3PO4. This is phosphoric acid. Right? And now this has 3 H's. All of these H's are attached to oxygens, which they can lose. So this is a triprotic acid, sort of unique in that example. We don't see a lot of those, right? So it's phosphoric acid. Both of these acids are weak. They're not considered strong acids. But as that trend, it follows the same trend where the more oxygens you have, the stronger the acid. So phosphoric acid is stronger than phosphorus acid. Well, these phosphate groups, the PO4 groups, we also call them phosphates, and they can form chains. So if we take one phosphate group and another phosphate group, and we can combine them at this point doing what's known as a dehydration reaction. So you take one hydrogen and one OH group, connect this bond to that oxygen in a sense, and you get out water, H2O. Right? And so that connects these together, and you can make long chains of these kind of inorganically. This is very important in biochemistry because molecules like ATP, which is adenine ribose triphosphate, can use these 3 phosphate groups. So these phosphate groups, on a molecule like ATP, you can have 3 of them together, and this forms a very high energy bond where it can be used as a way to store potential energy, right? And then reactions that cleave that bond are very, their delta G values are very negative, and they can be used to drive a reaction that has a very positive delta G forward. Okay, so you couple the cleavage of this phosphate group off of ATP. An example of that is glucose, the first step of glycolysis. Glucose has a phosphate attached to it to activate it, right? And so that normally, just by adding a phosphate group to glucose, that delta G would be very positive, but you couple it with this cleavage from ATP, and suddenly this becomes a very spontaneous process. Right. The phosphorus also has a cycle like carbon and nitrogen. We won't really spend as much time talking about it in this class. It's maybe a little bit more complex. But there are inorganic, land-based biological and water-based biological cycles within this. And so when we look at this, as you can see, it's a little bit complex, but nonetheless, it does have this natural cycle that's important. Industrial uses of phosphorus, by a vast majority of it, is used for fertilizers. Okay? The other smaller portions, phosphoric acid, and that's used for things like pharmaceuticals, detergents, food. So that's a pretty large part of the phosphoric acid production is used in those industries. You also can use it for metal treatment. And then there's elemental phosphorus, which is probably the smallest amount of what's used industrially. And those go into some special molecules, that production of those. Next element in the group, arsenic. Probably most of you know that arsenic is poisonous. Okay, and the poison itself is this arsenic oxide, and you can see, much like phosphorus and nitrogen, it can make these sort of larger oxide compounds. Right, and this is As2O3. It's colorless and white. Excuse me, odorless, not colorless, and it's white. And this is the poison. Right? It interferes with pyruvate dehydrogenase in the citric acid cycle, so that leading into this citric acid cycle. So if you go into biochemistry, that's a major biological pathway. If you interfere with that, you sort of shut down the cell. Okay. And what it's doing by doing this, it's inhibiting metabolism in a sense of everything, primarily sugars, but also proteins and fats. Okay, and this causes death. Right. So this is a common theme in some period shows. So the biggest example probably recently has been in Downton Abbey. It was used to kill off a character. The show referenced how she scrubbed her fingernails. One of the side effects of this poisoning is the discoloration of fingernails. So why was this used as a poison? Well, for many years, it was basically freely used because it was undetectable. So as long as you didn't get caught with it in your possession, right, or putting it in someone's food, it was very hard to tell that somebody had died because of arsenic. And that all changed with the what's known as the Marsh test, developed by James Marsh in 1838. Right, and this was the reliable method for detecting arsenic in the victim's stomach. Right. So what you do to do this is you use the victim's stomach, a sample from that, with zinc metal and sulfuric acid to produce what's known as arsenine gas, ASH3. So the oxidation that takes place, your zinc metal gives up electrons, so there's some redox going on in here, and reduction, the arsenic poison, As2O3, takes those electrons and gets reduced to As3-, which then can combine with hydrogen. If you have that acidic environment, it combines with hydrogen and you get this gas. Okay. And when ignited in oxygen, arsenic is oxidized to that solid arsenic, and that's what can be detected. All right, so here's our family portrait. All right, this one follows the trends much better than the previous couple families. Right, our ionization energies and electronegativities are all decreasing. Okay, although from antimony to bismuth, you sort of plateau out in electronegativities, but the ionization energies are all decreasing. Right. And again, here's a better look at what these look like. Right, you have nitrogen gas, colorless, it's gas. Phosphorus, there can be different forms of it. Here's red phosphorus and white phosphorus, arsenic, antimony, bismuth. Okay. Some reactions, right? We talked about nitrogen being fixed by the Haber process. That was an important one. The hydrides of other group members are formed by reactions of water or acid with the metal phosphide or arsenide. So this would be kind of an example of this for phosphorus. Okay, remember those other the other hydrides are very reactive and very toxic. Halides are formed by direct combination of the elements. So you mix one of these elements with a halogen and you get these halides. Right. More reactions. Oxoacids are formed from the halides in a reaction with water. So if you take your halide from this group, mix it with water, you get oxoacids. Okay, moving on to the oxygen family. Right, so here is the oxygen family. Again, these pictures sort of showing it as a liquid. Liquid oxygen, although we know it's a diatomic gas usually at room temperature, room pressure. Sulfur is this yellow kind of rock-looking substance, so it has a very unique color to it in its elemental form. Selenium looks just like a rock. Tellurium is now it's looking more shiny, more metal-like, but still not quite metal. And then finally, polonium is the element in this group that is the most metal-like. These all have the valence electron s2p4. Okay. So oxygen, like nitrogen, occurs as that low boiling point diatomic gas. Sulfur, like phosphorus, occurs as a polyatomic molecular solid. Selenium, like arsenic, commonly occurs as a gray metalloid. Tellurium, like antimony, displays network covalent bonding. And polonium, like bismuth, has metallic crystal structure. So you can see that group 5A and group 6A are sort of common. They have a lot of common features to one another. They're sort of similar. Right. We talked about some allotropes referring to phosphorus in the last group. Oxygen actually has some allotropes. O2, which we all know, oxygen gas, essential to life. It can occur as ozone as well, O3. And ozone is very important when it's high in the atmosphere in the ozone layer. When it's down here in the surface, it's actually poisonous and toxic to us. So it's part of one of the bad downsides to using ethanol as a fuel in gas, additive to gas, is that on warmer temperature days, burning that actually leads to higher ozone production, and that's occurring when you're driving your car down here on the surface of the Earth, and that is toxic and poisonous to us. So that's one of the downsides to that. When it's high up in the atmosphere, it's great. It helps us. It's actually very important to have. Just kind of juxtaposition there between when it's good and when it's bad. Okay. Sulfur has more than 10 different forms, right? So many different forms of sulfur, and that's because its ability to cantonate. Remember what that term meant when we talked about carbon? That's it bonding to itself, forming long chains and rings. Okay. Selenium has several different allotropes consisting of crown-shaped Se8 molecules, and we'll see some of those as well. So many different allotropes in this family. Here is sulfur in a crown-shaped, so this is the cyclo S8 molecule. So we mentioned selenium does this, sulfur can do this as well, and it makes this ring structure of 8 sulfur atoms, and it's referred to as a crown because it's sort of oscillating bond going up and down, or I should say a sulfur atom being up or down. Right. Hydrides in this family, well, we know oxygen's hydride, or at least one of them is very important, water, H2O. There's another one called H2O2, or hydrogen peroxide. Hydrogen peroxide is a unique molecule in that it's one example where we have oxygen in a -1 oxidation state. Right. Usually when oxygen is bonded to something else, its oxidation state is going to be -2, but now in the peroxide, it is bonded to another oxygen atom, so that's why there's a difference in oxidation state here. Right. The hydrides of other 6A elements are foul-smelling and they're poisonous gases. So H2S is the big example of that. It forms naturally in swamps from the breakdown of organic matter, and it is as toxic as cyanide gas. So it's a very, very toxic gas. Okay. If you work with things that produce this in the lab, or maybe just work with it itself in the lab, there's lots of precautions you have to do. Okay. H2O and H2O2 can both form hydrogen bonds and therefore have higher melting points than the other hydrides in this family. All right, the hydride bond angles decrease and bond lengths increase going down the group. All right, except for oxygen, the group 6A elements form a wide range of halides, so combining with halogens. Their structure and reactivity patterns depend on the sizes of the central atom and the surrounding halogens. As the central atom becomes larger, the halides become more stable. So as you go down that group, those halides are becoming more stable. The pattern is related to the effect of the electron repulsions due to crowding of the lone pairs and halogen atoms around the central atom. Right? This is opposite to the previously observed bonding patterns, where bond strength decreases as bond length increases. So that's just one sort of unique example of the opposite of a trend that we're used to. So photosynthesis resulted in an increase in the oxygen levels in the atmosphere. So in the early Earth, there was no oxygen around, at least no O2 gas, right? And very early organisms on the Earth got the ability to do photosynthesis, which was taking in energy from light from the sun, and then they could actually use water, H2O, as an electron donor and convert that into O2 gas. And very quickly, this became as the oxygen levels increased, oxidation became the major source of free energy in the biosphere. So actually combining oxygen with other molecules to generate energy. Right. Don't really need to know that. Kind of not really discussing this at this part of the class. Some of the other minerals you might be interested in, shown there, but again, we're really talking about oxygen and the oxygen family. And this figure from the book kind of shows you some fossils, if you're interested, some early fossils, kind of at this transition between the anaerobic atmosphere and an oxygen-rich atmosphere. Here are the abundances of some selected elements in the crust. Right, so it's very interesting to note oxygen as an element actually makes up about 50% of the crust of the Earth, which you might not think that, right? But it's in so many minerals that it makes up a huge percentage of this by mass. Okay, and some of the other elements listed here. The next highest one that you can see is iron, and that's only about 5%. So, oxygen at 50% is by far the biggest. Right, sulfur. Sulfur forms two important oxides. SO2. Sulfur is in the +4 oxidation state. It's colorless. It produces a choking gas that forms sulfur, or H2S, or metal sulfide burns in the air. Okay, so SO2 not that great. SO3, sulfur's in this +6 oxidation state. It has two important oxoacids, sulfurous acid, which is H2SO3, which is a weak acid, and sulfuric acid, H2SO4, which is a strong acid. Right. And then this is just a picture in the book, kind of funny, but it's a dehydration of sugar by sulfuric acid. You have a sugar here, solid, you pour some sulfuric acid on it, and you get this dehydration reaction out with this steam coming off would be water vapor, and then you're left with this kind of black stuff, which is just the carbon that's left. Selenium. Selenium is kind of interesting. There's was used in semiconductors, but that has been overtaken by silicon. Chief commercial uses now are glass making and pigments. It is toxic in large doses, but it's also an essential, what's known as a micronutrient for animals, so we need this. And why we need it is it's a component of some of these what are termed as unusual amino acids, selenocysteine and selenomethionine, where the sulfur in the normal sulfur in the amino acid has been replaced by selenium. And it involves, it's used in enzymes to reduce hydrogen peroxide, which is very reactive and damaging, into water. Okay. Polonium. Polonium-210 was discovered in 1898 by Marie and Pierre Curie. Okay, it was extracted from uranium ore, and it was identified basically just because it was so radioactive, and that was the first element to be discovered that way. It's an alpha emitter that has a half-life of about 140 days, so that's pretty short. Polonium-210 is very deadly. It's a very deadly poison, and it has been used in assassinations before. Mass polonium-210 is one of the deadliest toxins. It's around 250 billion times more toxic than hydrogen cyanide. So that's a crazy number, just how toxic this stuff is. Luckily, the natural polonium is very rare, and that's because of that very short half-life. As little as about 100 micrograms of polonium occurs in 1 ton of uranium ore. So that is another crazy number, that you'd have to have 1 ton of ore just to get out 100 micrograms of polonium. Okay, and that makes it all, I think, more, what's the word I'm looking for? Just how amazing that feat was to actually purify it and identify it by the Curies in, before 1900, because there is so small amount of it naturally. Right, so here is our family portrait. Okay, again, now we're getting to where the trends we are really following, where electronegativity and ionization energies all go down as we go down that group. Okay, and you can see that the elements in the group themselves vary. Just the look at them varies quite a bit. Okay, some reactions that are important. Halides are formed by direct combination of these groups. So you mix a halogen with it, and you get some various halides being formed. Other elements in the group are oxidized by O2, the top element in the group. So you combine any of the elements below oxygen with oxygen, and you get oxides. Right? SO2 is actually oxidized further into SO3. Right? Thiosulfate ion is formed when an alkali metal sulfite reacts with sulfur. So we have S8, that crown-shaped orthorhombic sulfur, mixing with this sulfite, and we get what's known as a thiosulfite with the S2O3. Right, that finishes up those two groups. The next lecture will be the last lecture, and we'll be discussing groups 7A and 8A, the halogens and the noble gases.